nights, I think. That was the only time I have with Brunei. It is a very beautiful country. So I love it very much. That time I was working in University Malaysia Sabah. So I drove with my family together with 5 of other of my of family members. We drove from Kota Kinabalu to Brunei, and I think we passed about 7 checkpoints for immigration before we reach Brunei. So it was very nice country. I love it. Very clean, very organized. Oh, fantastic place lah, fantastic place. So I think thank you to Dr. Zunaidi. Thank you to Dr. Zunaidi lah for allowing me to share with you. Okay, as you know, let me share my screen lah. I think you have seen enough of me. I'm already going to be 62, so I'm not young. I'm not as young and as dynamic with Dr. Zunaidi. I know Dr. Zunaidi. I remember very well. I first interviewed him in a stall, in a roti canai stall. If you remember Dr. Zunaidi, I remember that time. The first time I met him already, I'm very impressed with Dr. Zunaidi. So that's why we took him to join University Malaysia Police, and then his color flies everywhere. I know he was in Terengganu as a rector, and he was in the UK now. He's in Brunei. So I'm not surprised. I'm not surprised that he will be a very important person in Brunei. So one day he will have the title of a Pehin. I know that, inshallah. Okay, maybe can I know how many of you here? Only I can see only 4 names. Is it correct? Is it only 4? Only 4 people?
No, bro, we have 25. I think now in the screen, in my screen, around more than 10.
We were sharing, sir.
Yeah.
Okay. Because I thought I saw this big screen. I can see only 4 names like Wafid, Samford, Shami, and Bazila, or more than that. Okay. All right. So the next thing I'll do, I'll share my screen. Okay. I used to use Microsoft Teams and also Google Meet. So this one, sometime, if anything, please help me. Please help me so that I can. So okay. Okay. So, oh, sorry, I should not do that. I should cancel it. So can you see my screen now?
Yes, Prof, can.
Okay, this is the screen. Industrial Control System and PID Controller. This is my name, Dr. Sazali Yaacub. I'm a head of Intelligent Automotive System Research Cluster for Electrical, Electronic and Automation section. And Alhamdulillah, from October last year, now I'm the Dean and also head of campus of this Malaysian Spanish Institute, University Kuala Lumpur in Kulim, Kedah. So Kulim, Kedah is the northern part of Malaysia, and Kulim is the biggest industry park, the biggest industry park in Malaysia. Okay, it's covering about 20,000, about 10,000 acres of industry park. So it's very big areas. So it is very interesting also to be working here. And for your information, University Kuala Lumpur have 12 institutes, and we Malaysian Spanish is one of the institute. And our focus is on automotive. Okay, in automotive. So I think the title of control system and PID is something that it's very interesting because I did my PhD also in control engineering. So I think I can share. And I made to understand that most of you are third-year students. So I hope I can explain some theories about control theories lah. I must tell you, control theory is not a very interest. It's a boring subject lah, I tell you, because a lot of maths, a lot of abstract understanding. So by all means lah, please treat this session just like another lectures lah. I would welcome very much questions and answers lah. Okay. All right. Okay. Without further ado, I will present my lectures. But as I said, I welcome questions and answer during any session. Okay. Okay. The content I will try to distribute this. I don't have the syllabus of your subject, but I think I will try to give you something in general. Okay. I will talk about basic control. I will talk about compensator. I will talk about digital control also. Because I think before we go to industry control, we must understand what is digital control. Because like it or not, I'm not sure it will cover in the syllabus of a third year, especially for the mechanical. But if you're taking a control subject, digital control is very important because everything now start with digital. So you must understand what is digital control is all about. Okay, and then I will try to talk a bit about industry control, just to link with the titles. And finally, I will talk a bit about PID controllers. Okay, is everybody okay with that?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, good. I'm very happy to see that you are very dynamic. You are all potentials of Brunei's leaders and engineers. Okay, let me talk about basic control. Okay, as you know, control theory it start way long ago, before 300 BCs ago. That time you have water clock, steam pressure control in the 60s, and then the speed control in the 18th century, and then control theory start to come in only in the 19th century, meaning that control has been synonym in our life, and it has been there for years, but the theory was only developed in the later stage. And the understanding of the control theory is very important, because control theory or used to be called as a system theory. Okay, so when you're talking about control, you're talking about system. You cannot run away from that. And when we talk about system, it can be in many type of a system, either economic system, either industry system, either in the automotive system for that matters. So anything is basically system. And basically you define yourself what is the system you're talking about. So in the 20th century, we're talking about automatic ship steering. Then the PID controller come in the 1920s. And then the feedback control theories come in the 1930s. And then you get more theories about road lockers, bot plot, and the Nyquist. But I think the theory was then happened, and it's going to be very difficult because there is no competing powers. But now with the competing powers, you know that you can easily use a MATLAB. I'm sure you're using a MATLAB software, isn't it? So a MATLAB software is a line control. It is making your life easier. But I think despite that you have this MATLAB as a computer-aided design, the control theory must be really adapted, because once you have a strong control theory, you can adopt it in many other applications. That's one thing I must tell you. I must admit, when I was a student like you in the third year, I learned the first time about control theory. I found it is very difficult, but I think you all are very fortunate to have Dr. Zunaidi. He's a very experienced person, so he can relate in many applications, even more than me, because before he joined in the academy, I'm sure he worked in the industry, so he can do better job than me. However, I will try to share with you lah. Okay, and contemporary, the applications start for navigation, entertainment, smart home, military, space application, chemical process, and also in automotive and in any dynamic system. Okay, so you see that this control theory has been evolved before the 300 BC itself, and it's been now, and it's still very relevant now when we talk about Industrial Revolution 4.0. It is all can be use control theory into the elements. Okay, it's very important. first I talk about human control. I mean, when you're talking about control, you're talking about about anything. It can be also about human. So you see that if you want to ride a bicycle, you have to know how to control the handles. You have to know the dynamics before you can have the stability. If you fall down from the bicycle, it's considered that you are not in a stable condition. So that is the first thing about control. Safe is there. And then you can see this type of control in many applications in your bathroom. You can see this flush principle. It is being used until now. Okay, you have a float, and basically when you flush down, the float will come down, and that float basically will control the valve, and the valve is open. You know, some people may feel that control theory is related to electrical, but it's not true. Control theory start from mechanical actually. In fact, the oldest profession in engineering is mechanical engineering. So that's why being a mechanical engineer, you will be much more respected because you are considered a very general engineering. Because from mechanical engineer, you start come off all these civil, chemicals, electricals, or even electronic. Okay, so if you see this manual control is all about mechanical engineering, mechanical principle. So I think I have a lot of respect and regards towards mechanical students or even the lecturers. Okay, and then here again, here you can start to see that you have this example of a control by using a visual inspection. So if a person see that the levels of the tank is to the required value, it will either control the valve, whether will allow the water to flow or just stop it from there. So as we grow further, we are not using human control, but maybe we use a controller. This is where the industry control comes in. Okay, so you see that you can have this water flow, whereby you can control the water outlet, and not only that, you can even control the temperature of the water tank. So you see that in this kind of a system, it can be either you want to control the levels or you can even control the temperature. This is the case whereby you have more than one variables. Okay, before this we have only for level, just one variable. Now you can have even two variables, and this is what we call as a multi-input and multi-output, because you can control either the flow and also the steam temperature. And you can control the steam of this coil. Jadi this is one of the example that we call as a multi-input. Okay. So far, okay. And do you get what I want to show here? So meaning that if you look at here, you have only single input and single output. Okay, the input is this flow, and the output is what is the required level. That is called single input and single output, or they call it as a SISO. So here you have a case of multi-input and multi-output, whether you want to control the level or you want to control the temperature. This is called MIMO, multi-input, multi-output. So this is in fact the industry control. Because when you talk about the industry control, you're not talking about single input and single output. You're talking about multi-input and multi-output. And of course, I tell you, the theories of multi-input and multi-output is not easy. The mathematics is very, very tedious. But never mind. I just want to share with you what we talk about industry control here. So basically, you will have a controller 1, okay, for the temperature. Another controller is for the water level. Okay. And as you see that here, they use more industrial controller by using a manual water regulator, a flow transmitter, a measurement for the control valve, and they want to control, for example, the magnetic flow meters for a tank. Okay, so meaning that as you see that as mechanical engineers, you should be very well versed with the system. Okay, so as I said to you earlier, when you talk about system, it originates from the mechanical discipline. Okay, this is another examples of using a control valve. So here you can start to see that people start to use a PID controller, for example, and then you have a flow transmitter, you have a control valve to control this one. So now we're talking about people are going into the automotive control. So this is the examples of using a different sensor, using a capacitor probe and a controller and so on and so forth. So this is another system also. This is called FMS, or flexible manufacturing system, whereby you can use for pick and place, you can use a robot, you can use many aspects just to control things. This is another examples of force control. You just see for this robot with the end manipulator, you have a force sensor. So basically, the manipulator will follow the gradient of the surface. So for this, you need control. And again, this can also be part of the industrial control in certain application. This is another control that people use vision now. People use vision control for this bin picking. Okay. This is another control for a sound control, meaning that if you hear before the controller, the noise is higher, but after applying the controller, the noise will be lesser. This is also a type of a control. And then if you're talking about automotive industry, they want to cut down and to give comfort to the driver, they may use this active noise control or active noise cancellation. This is another thing about satellite control. What I'm showing here is examples of application that I work with my students for their master or for their PhD degrees. This is another example of a process control. A process control where you have what we call as a pilot plant. Okay. This is another control, we call it as a fast control, or sometimes in control we term it as a servo control. In fact, in control system, there's two types: fast control or slow control. Like this process is called slow control, or another name they call it as a process control. For a fast control like this, they call it as a servo control. Okay. Of course, we can use a control system also for a steering control system for a car. Okay. So you just imagine, without the control system, you will not have a desired direction of travel as smooth as the blue color. Okay. I want to demonstrate to you a simple system. This basically a turntable. You may not see this thing anymore, but when I was before I reached my teenagers, before I reached my way back in the 1960s, when you want to hear music, you use this record. Basically, for this record, you have a turntable, and then you have this stylus that will sit on this record, and according to the groove of the surface, it will give you music. But now you have a digital audio. Basically, it translates into 1010 only. But during my time in the 60s, you hear music using this record player. So now this is considered antique. But during my time, this is considered luxury items, you know. Not many people even can afford to buy this. But now it become into the museum lah. Okay. Basically, when you have this turntable, you can represent it as a schematic diagram like this. But then you want to show as a control system what is the block diagram. So you translate the amplifier. This is the amplifier. This is the motor, and this is the turntable. And your input is required speed, and your output is the actual speed. Okay. Of course, this is considered open loop because once it is turned, it will not give you any feedback. So this is termed as open loop. So basically, in a control system, you have two types: open loop or closed loop. Of course, when you have a feedback, you use a tachometer to determine the speed. So this we term you as a feedback control. Okay, you will have this feedback using this tachometer. So you see that as a control engineer, you must able to translate the functional block into a block diagram. So from the block diagram, then you can apply your control theory. Okay. So this is the control theory that you can think of. Okay. And then of course now, this is my first master student. I was working with him in the 90s. That time, computer control is considered new. So basically, we use a desktop then, but now people use microcontroller. People use a single board computers. But technology has moved so fast. So basically, this is a work to control this speed of this induction motor. So you see that we use the input that is controlled by a frequency inverter, and we measure the load by using a magnetic powder brake, and then we use the interface data to get this data. Okay, so basically when you're talking about control, you must talk about better sensors, better actuators, and that will give you a better control. So this is the part. And then when you talk about control also, you want to know this response. Basically, in a control block diagram, you can represent it. You can represent this one, all this block into a transfer function. And that transfer function is originate from a differential equation. And the differential equation is either first order, second order, or higher order. So basically, when you talk about control, you want to see the response. So, for example, I'm sure you learn in the control theory yourself. For the first order, this is the kind of response you get. So from here, we give some parameters to that. This is a response of a second order. Depending on the poles and the zero position, you get the various type of response, either under damped, over damped, and critical damped, as shown here. This is a second order, depending on the damping ratio. Of course, you can see that the position of the poles can designate basically your response. Okay, and you can see this from the book. And I'm very happy to answer you if you're not sure of any of the slide. Okay, so I want to show you examples of a control theory. If you have a pulse on the left of J omega axis, you have a system which is called stable. But if you have the pulse on the right, the response will not become stable. Okay, and then in a control theory also, we talk about response. We talk also about steady state. Okay, so one of the parameters we can use for measuring a steady state is the steady state error. So these are examples of first order steady state error, and this is for a second order. Okay, and then basically from here, we can use a table that we know from for a step and ramp to measure the steady state error. So I think basically I covered the first part. I think before I go to second part, I want you to relax. So one way how to relax thing is to ask question. So you have any question to ask so far? Or you feel that you have covered this one, it's very easy, you can tackle it, or you want to answer question before we go to the second part? Because if I were to go second part, I'm worried that you're going to get lost or you may get bored. So I want to know also the speed of your understanding before I go further. Any question? Hang on,
No, sir.
There's no question, huh? Okay, I just take my drink for a while. I forgot to put a bottle next to me. I just take my drink for a while. Huh? Okay. Just give me a short while. I just take my water.
If you have any question, you can write down in the chat also, chat board here, or you can ask directly to the Prof.
Sorry about that, because suddenly when I speak so much, I get my throat become dry. Let me drink for a while. Okay, is there any question that you want to ask?
Sir,
Yes.
can you go back a few slides just now for the
This one?
wait, where are the slides? A bit more, sir.
A bit more, okay.
Yeah.
This one?
Yeah. Can you just explain a bit more about this one?
Oh, okay. I will explain you a bit more about this one. Okay. First of all, you must understand about pulse and zero. You all understand about pulse and zero?
Yeah. No.
Not much. Okay, never mind. Okay, if you look at this transfer function, okay, you have the top and you have the bottom. Okay, correct? So the top part here, we give you the zero. But in this case, there's no zero lah. But if you look at the bottom part, the root of the bottom part, we give you a pulse. For example, the pulse will be 0, will be -1 and -2. And the closed loop of this is the pulse. So the position of the pulse is very important to determine when you talk about a response, you're talking about two parts. You're talking about transient and steady state. Okay, transient and steady state. For example, when you have a response like this, okay, you see that it is oscillating, correct? Correct or not?
Yes.
Okay. This oscillation is called transient, meaning that, and if you see the second part, the response become steady, and this is called steady state. So basically, in a response, you have two parts. You have the transient part and the steady state part. Okay, and the behavior of this transient and steady state is very, very much affected by the position of the pulse. If your pulse is on the left of j omega axis, then the response is considered stable. If it is on the right j omega axis like this, it becomes unstable. But the pulse also have influence on your transient behaviors, and also due to the pulse. So when I show you this one, it shows that if the pulse move from position 1, 2, and 3, meaning that it's moved away from this axis, you see that the response become very overshoot is higher. If the pulse is moving to the horizontal, you see that the response will become more oscillatory because the natural frequency change. And if you see that the pulse move diagonally, the damping ratio remain the same, but the natural frequency will change. Meaning that as a control engineers, you must understand. You must understand what kind of response you are talking about. You must understand the position of the pulse you're talking about. From that understanding, then you can know what kind of response your system will generate. So this is very important when you apply in other application as well. So what I want to say here is that the position of the pulse will determine the behaviors of your transient and the behavior of your steady state. Okay? Very good. Any more questions? Okay. If not, I go to the second part of our lectures. Okay. I go into the compensator. What is compensator? Basically, a compensator is that, as I showed to you, you can have various type of a response. In order to change the response or the position of the pulse, you have to use a compensator, or people call it sometimes as a controller. So basically, when you're talking about compensator, you're talking about here. See, this is your plant. That's why when you learn about control theory, first thing you must understand about block diagram. As I said to you, it will consist of a plant. Okay. It will consist you of your feedback, or in this regard is your sensor, because you want to measure the values of your output. So you have a sensor. And then you will have also actuator. Actuator is basically to drive the plant. For example, if you want to control the water level, so the actuator will be the pump. Okay. If you want to control the temperature of your water tank, so the actuator will be your heater. Okay. So before your actuator, you must have something that want to control this process, and this is called compensator, or people sometimes call controller. Okay, doesn't matter lah. But some books will define controller to comprise of compensator and actuator. So that's why this individual controller like the PID is actually a compensator, but some book they call it as a controller. Doesn't matter lah. But because some book they call controller as the compensator plus the actuators. Okay, so that's why for me, not to confuse you, I will say that controller is made up of compensator and actuator. So when we talk about PID controller, what I'm referring to this is actually PID compensator. Okay, so basically here we see that actuator takes low energy signal to transform to amplify before going to the plant. Okay, because your controller here may have a low energy. So basically actuator will transform that before you get to the plant. And the sensor take high energy from the plant and transform to the low energy for further action. Especially when you talk about computer control. Computer control cannot take so much voltage and current. So this is where the sensor will basically play the roles of signal conditioning. Okay, so there's many issue about signal conditioning. Even I will tell you, student, as a mechanical engineer also, you must be very well versed with the microcontroller, with sensors, because as I said to you, people will look for generic discipline. So you must know also in other fields. So that's what I'm saying. Okay, basically, when you talk about this compensator itself, it can have in many forms. For example, we call it as a forward pass compensator, when you have the compensator to be here. And this is your basically actuator. This is your plant, and this is your sensor. So this is called forward pass compensator. Okay, basically it's used for because it is easy to implement. Another form is called feedback pass compensator. So you have your compensator to be here. This is important to avoid a time delay because you know for the processing here, you need to basically control it because this will also take time, so that will create a time delay there. And this is basically to avoid time delay and lag. Okay. And then you have a feed forward pass compensator. So feed forward compensator is that you have a compensator here, meaning that you can anticipate what is the disturbance. For example, you want to get. For example, for this product graph, you have the required and the disturbance. So you anticipate the disturbance. So basically, it's used to absorb for disturbance. Okay. And then you have an inner feedback loop, also known as a cascade control. Okay, you have this cascade control used to eliminate minor disturbance. If you have disturbance, it will try to tackle it in this loop. And then you have also a velocity feedback. A velocity feedback is known as a rate feedback you have at the plant. Is to overcome the feedback of instantaneous changes. So basically, as a control engineer, the selection of compensator, you must know according to the flow problem, the level, the temperature. Okay. So if you're talking about flow, you're talking about very noisy, thus you need a derivative action. And you're talking about level, you must talk about proportional action. And temperature, you must use PRD. We'll talk about PRD later. So basically, that finished our second part. I tried to finish before so that I can give you a chance of 30 minutes to ask me a question about the overall presentation. Okay, so far for the second part, is there any question? Okay, if there is no, I will move to the next part. Of course, reserve it, and we try to have more bilateral communication after this, okay? Now, I want to talk to you about digital control. I think you may have not, have you learned about digital control or you've been studying it in a subject? Can I know what is the feedback? Have you heard about digital control?
Yes, sir. A bit here.
Stephen, have you heard about digital control?
A bit here, sir. A bit
What?
here and there, sir. A bit here and there, sir, about digital control.
Stephen, can you repeat? Stephen, I cannot hear you then.
Yes, sir. We know somewhat about digital control.
Have you learned a subject in digital control?
Technically, maybe somewhat into digital control. We did learn through different modules about it.
Okay, then one. Okay, if you have learned something, then okay. I will try to say something. What is digital control? What we have covered before is normally people call as a analog control. So you use Laplace transform, isn't it? Okay, you know what is Laplace transform? Laplace transform is basically converting from the time domain to the frequency domain. Okay, that is analog. Our physical world is analog, but our computers, microcontrollers, is digital. So having a digital is not all rosy. There's a lot of thorns there. So it's not easy actually. Never mind, I will share to you digital control. So you see that digital control is useful due to the advance of computers. I remember when I did my master's in 1986, you were not even born. I think that time Dr. Zunaidi is only maybe 13 years old lah, maybe, Dr. Zunaidi?
Prof.
Because I know Dr. Zunaidi born in 1973. Correct, Dr. Zunaidi?
73.
Yeah, I know, because he's the same as his many colleagues in University of Metropolis, like Professor Hazri, Dr. Shariman. Okay, never mind. So that time, you know, I remember my first computer. My first computer, that time in Malaysia, there is no computer yet. There is only mainframe. The first desktop I have is when I did my master's in England. And believe it or not, the RAM size is only 256K. Not M, K, K only. And and then of course the biggest hard disk that time is 20 megabyte. And I cannot afford to buy it because it's very expensive, 20 megabyte. So now easily you can have 2 terabyte. So you see that the speed, I remember the clock speed is only 16 megahertz clock speed and only operate at 8 bits. Now you're talking about 64 bit operating at what, 3 gigahertz speed. Oh, fantastic. So it's been very fast. Huh? But because of the advent of computer, this digital control is, in fact, it's already common in the industry. So when you're talking about industry control, you must understand first what is digital control. If you just learn the industry control, but you don't understand the control, something is not right. And as an engineer, you must know this one. Okay, computer is used in the converting from the digital to analog. We assume that the number of or leave the computer at the same as the period sampling, because when you're talking about converting analog to digital, you must have sampling. Okay, and the advantage of digital control over analog control is very flexible, low cost, robust, and it is not sensitive to disturbance, and in terms of accuracy. Okay, and configuration of digital control system is like this. Okay, you see that before this we're talking about plant, we're talking about sensors, we're talking about controller, correct? But now, because of conversion from this analog to digital, this analog signal from the output here and the input also is analog, you need to sample it. So sampling is converting the analog to digital. Okay, and then you use your controller, and of course after your controller action, you need to convert back your digital into analog, because your plant is a physical plant, and the physical plant is an analog signal. So this is where we use digital to analog converters, just to convert the digital signal to the analog. So another form is that this is one form where the input is analog, but you may have an input which is also digital. So for that, after your output here, you must use a analog to digital converter to convert the signal of your output so that it is compatible with your digital input. Okay, this is another form. Okay, this is just to show you the various waveform. Okay, you see that your plant, which give you an analog signal, you go to your transducer or sensor. Sometimes people don't call sensor, they call transducer or feedback. It is the same thing also. Doesn't matter, because I take this from a different book, so they just put it transducer, but it's okay. I'll tell you, transducer, sensors, or feedback is meaning the same thing actually. So basically, it get you the input analog signal, it compare the two, and then basically you use a sample and hold or sampling, or they call it sample and hold, and it convert into these digital numbers, 010. It go to your digital computer. Of course, all this must be synchronized with a clock. And then from the digital signal, you convert the digital signal to a analog converters, and you use a whole circuit. Basically, a whole will hold the signal so that it become continuous. If you have a signal like this, it's called discrete. And your actuator cannot accept discrete signal. It's like only a pulse. Any physical system cannot accept a pulse. If you accept a pulse, you have a problem in terms of the lifespan of the physical system. So it uses basically a whole circuit to hold the signal here, and then it uses actuator and to drive this back. So this is a good example of how does this analog and the digital things comes in. Okay, I will show you how to convert this analog control into a digital control. For example, this is a good example of simple analog speed control system. A simple analog speed control system. Excuse me. I'm very excited teaching you all, so my throat become dry very fast. I don't know why. Maybe I have a lot of respect to Brunei people, you know. So that's why I get very excited, and I'm very happy to see my good friend Dr. Zunaidi there. I really miss him actually. I've not been seeing him for some time already. Okay, and I feel that you are very fortunate to have him lah. I wish that I can also learn under him. I know he's a very good person. Okay, let me continue. We have a simple speed control. You have a motor, and a motor use a tacho generator to measure the velocity. And basically, this analog signal, we go to a difference amplifier, and you get the input of the speed using a potentiometers. And then basically, the different signal, we give you this power amplifier, basically to control the motor. It's simple. Very simple speed control block system. Very simple. Okay, how you convert this one into a digital control? Of course, your tacho generator will give you an analog signal. So for that, you need to convert the analog signal to digital signal. So this, you use an analog to digital converter. Okay, and then this is your computers. Basically, you can set in the required speed by just key in button, which is a digital signal. And then when you get the computers to do the computation or the control action, then you use a digital to analog converter to go back to here. So you see that? You see that an analog has this system and digital has this. So digital in this regard has more components to be involved. And fortunately, the component now is cheap compared to previous time. But by having this extra block, in fact, it creates more complex variables. So that's why having a digital control also is not easy, because you introduce many non-linear effects, and that can become a deterrent to your control action. Okay. So digital control can perform as either supervisory. Basically, external feedback loop is scheduled, and this is where it's going to relate back to your industry control, which we're going to cover in the later stage. And then the control is basically the internal feedback of a loop. So this is another examples of angle control. So for the analog, for example, you want to control this antenna, you just vary the potentiometer, it will go through. But under digital, you must have this analog and digital converters. Okay, in order to use digital control and signal conversion, it's required placement of the computer in the loop and the detail AD and DA. This is just another examples of a block diagram for this analog to digital. This is also another examples of a closed loop drug delivery system using a digital control. You see, basically you have a drug pump, you have a patient that going to be controlled in terms of the drug into the patient, and you want to measure also the blood sensor, whether they think it's affected or not, and you use the digital control for this. And basically this schematic diagram is converted into this functional diagram, okay, into this block diagram. So you have this in the patient, This is the drug pump. This is the conversion of computer DAC, and this is the computer control. This is the sensor. So you see that in order to have a better understanding about your control system, you must translate that schematic into the block diagram very well. Then you can understand better what you're talking about. So this is another example of our aircraft turbojet engine control. Basically, you have a DAC and ADC. You have an aircraft, you have a turbojet engine, and you have the engine sensors. This is another examples of a robotic manipulator control. Basically, you want to control this the manipulator, you want to control either the position or the velocity of the robot. These are another examples of a missile guidance system. You have this missile, you want to control this guidance using the tracking data, and the missile have to move very fast. So that's why you have the acceleration, and you use AD and DA. So this is to show that this AD is translated in block diagram as a sampling, and this DA is by this whole circuit, and this sample is be here, and basically this one can be translated into this transfer function. Okay. Okay. Basically, we finished the third part. We have only two parts to cover, which is the industry control parts and the PID parts. Any more question?
No. Not for now, sir.
Okay, we just finished about 1 hour and 10 minutes. I will finish another 15 minutes, then we will have a good question and answers. I will be very happy to receive question, and then I try to relate your understanding from that question and answers. Okay. Okay, let's go to the industry part. So basically, industry control system is is the control system of instruments used for industrial process. Okay. So it has many forms. It has what we call as a process variable. It's a set point variable, and it uses what we call as a final control elements. So basically, in a control theory, the output is called output, but in industrial control, they call it as a process variable or PV. The input or the required value, we call it as a required value, but in this industrial control, they call it as a set point. And then they use all these actuators, and here they term it as a FCE or finite control elements, such as control valve, for example. Basically, in a larger system, what I presented to you just now is only a simple system, but you can talk about a very big and complex system, and for that, a lot of data can be come in, and this is what we call it as a SCADA. And basically, from the data system here, it can be divided into either distributed control, PLC, and also RTU. I will tell you one by one. Okay, basically discrete control is what I have described to you earlier. Okay, I've described to you earlier what is discrete control, which is something they call as a digital control. Okay, this is one of the RTU unit they use for the PID control. Okay. Okay. Now they use this what we call it as RTU. So basically, you will have all this flow transmitter, and the flow control valve is controlled by this RTU, they call it, or remote terminal unit, or RTU. Okay, basically this remote terminal unit will give you all the communication with the actuator. You have either the input and the output which get to the data in. Okay, and then basically this will do this control. So when you talk about industrial control, normally they use only on and off. Okay, because for industry, reliability, repeatability, robustness is very important. In a control theory, there's so many theories, so many mathematical involved. But the industry would prefer something that which is simple. which is easily to operate, which is easily to detect, which is easily to implement. So that's why a popular industry control is just a on and off control. That all people call as a bang control. Okay, so it's simple. One unit control is RTU. Okay, basically it control what is the current there between 4 to 20 milliamps. Okay. And then if you have a more complex system, then it can be, this RTU can be grouped, and this is what we call as a distributed control system. And if you have a bigger one, we will call as a SCADA, not only control but also for data acquisition. This is called SCADA. So SCADA stands for supervisory control and data acquisition. Okay, so it can even have a graphical user interface. It will have your PID and your PLC. So this is examples of a very distributed control system. Okay. So you see, basically you see that this is your plant. This is your microcontroller, or they call it as a RTU. And this is the computer that basically control the various unit of the RTU. And then this we control into the center or the command value. So you have a very level of production levels from level 0, 1, 2, 3, and to level 4. This is basically what is the industry control. So you see that when we talk about industry control, it's more of using a control theory and getting something done and then interconnect it. That is more of what they call it. So this is another example of a SCADA. So it looks more complicated because it involves thousands of output and maybe hundreds or maybe tens of input. So you can see it is become a very much more complex things. You see. So you see that this is where your control center, where you get your human-machine interface. This is where your SCADA, this is your communication router, and this is where your field bus, and this is where your modems to communicate in betweens. Okay. Okay, this is just examples of pictures of your SCADA system. And before the SCADA, you have also PLC. So again, PLC is just basically this RTU for on and off. Of course, it has many switches. So basically, a PLC is a programmable control of industrial control that has ruggedized and adapted for control of manufacturing process such as assembly, robotic devices, and activities that require high reliability, ease of programming, and process fault diagnosis. Okay, these examples of PLC, and this is what I call to you as the RTU. It's used application in remote location. This may include water and offshore. Okay, so now I come to the last part before we go for question and answers. PID controller. Okay, again, I like to share with you some simple block diagram first. This is your plant. This is your controller. This is your feedback. So basically, you can see from control theory, your controller is, let's say, it's a proportional. It's just a gain, KP, and your output of your actuators here is basically the error signal multiplied by this one, you get this one. So basically, if you can give a high value of KP, it gives you a good steady state area, but it has a poor transient response. And too high of KP also because instability. So this is as simple as a way to show to you how does this controller function in order to reduce the error. Basically, you will have a transfer function of this system to be like this. And I'm sure you have learned about Mason rule. So basically from here, you can get your transfer function. And from there, you can determine your final value by using final value theorem. And then you get finally this value. So you see that if KP is big, and this KP is big, and F is a friction, of a motor, it can be low as you control the friction. If Kp is very big, so the value is 1, meaning that you don't have a steady state error. This is the proportional. In order to get a real zero steady state error, you use an integral. You use an integral controller. So in an integral controller, basically, you have the same block diagram like this. Okay. And then basically you have this controller signal here. And then this is the actuator signal, which control the output. But the problem with integral control is very slow because it sum the error. It do iteratively, so that's why it becomes slow. But it will give you a zero steady state error. How? This is a simple example. Again, the same system, but now you have an integral effect. So if you use the transfer function, you use the final value, you get a value of 1, meaning that there is no steady state error. Whereas in the proportion just now, it depends on the value of Kp. Okay. And finally, you're talking about this derivative. So in derivative, basically, the good thing about derivative is that it will reduce the rate of errors. In proportional and integral, it reduces the error, but this one, the rate of errors. So it can cut down any oscillation, any overshoot even faster. So the answer is quick response, no effect at steady state because of no error signal, and useful for controlling the type 2 and above for control. Okay, basically a combination of proportional and integral, you can get PI, and you can get this kind of transfer function. Or another form, it is be something like this. And I'll give you an example of PI controllers. You will get a zero steady state error. You know, the integral will get you also a zero steady state error, but it is slow. But using a PI will be faster. Even if you want to be much faster also, then we use a PID control. Okay, this is examples of transfer function of the PID controller. Okay, and how to tune this PID control? There is two methods. They're called as a Ziegler-Nichols method, basically, or it's called as an open loop method. So when you have this response of the open loop, you will get this kind of a response. And from here, from this response, we measure certain parameters of K, which is the DC values, the L, the delay, and T is the rise time constant. So you will have a parameter of K, L, and T. From that, you get a parameter called A. And from here, you can use a table to determine your PID values. That's how people do in the tuning. But please remember, tuning in this method is only an approximation. You have to do a fine tuning using either manually. Okay. And then the second method is called the closed loop method. It's basically looking at the stability gain and also the oscillation time. And it is given by this table. And for example, this is a simple transfer function. From this transfer function, you can determine the characteristic equation, and you can use a route array. And from the route array, you can measure of your K and your T. Okay, basically you get your K to be 10. Of course, this is a theory there. I'm sure you have learned also about this, but I just want to show to you later. And this is the kind of response you can get from the P, the PI, and the PID. Okay. And then, of course, now people use the PID controller using a Simulink. So you see that in Simulink, basically you have your proportional, your integral, and your derivative there. Okay, and basically, you can see the response in Simulink of a P, of a I, and of your PD, and your PI, and your PID. But the best part is that you can use a simulation block, and then you can do the automatic tuning. And from here, you can get the best tuning effect. That is from the MATLAB. Okay, I think I have presented to you nearly 1.5 hours, so I know you get tired of it as well. So with that, I finish my lectures here, but I want to open, we have about half an hour. I'd like to open it for question and answer, so that we can recap back and look at things that you may not be sure. I think Dr. Zunaidi, I finished my parts here. So I think I will I leave it to you lah, how to make this question and answer session or what. Thank you, Dr. Zunaidi.
Okay, thank you, Prof. Thank you. So I think you all guys can ask Prof the question. If you don't want to use your mic, you can just use the chatting box there to ask the question.
Oh yeah.
Yeah, you can ask through that one also. I can read through the question, and then Prof also can read through.
Yeah.
Then,
Okay. I can see it.
So at the one, you can on your mic to ask. So we wait, Prof, some question from
Please,
the student.
if you want to repeat any parts of the slide that I present to you, I will do so. So that's why I was a bit rushed in presenting, because I want to give more time for you to ask questions. Because you will understand more if you ask questions. If you don't ask questions, then I'm worried about your understanding. So by all means, please. I also open the chat. So if you want to put a chat there also, I can read it out, and then not need to read, you also can see it, then I will try to answer from there.
Steven, Nazirul, others, please ask. If not, you need to go to UniKL to ask the question. Now Prof already here. No need to come to Brunei.
If you want to do master or PhD with me also, you are most welcome.
Yes. Okay, Prof, I think one question.
Okay, regarding the compensator, can you
Steven,
explain more about the situation where you use which compensator type? Okay, very good. Regarding the compensator, can you explain more about the situation where you use which compensator type? Okay, very good question. So my answer is like this. Okay, when we look at the slide of this compensator, okay. It's all depends on what type of problem you want to tackle for. I mean, for example, if you're talking about a simple implementation, you use just this forward pass compensator. You put the compensator here only. Okay, so you can play this one with your MATLAB. But if you were talking about to avoid a time delay, I mean, maybe your system here, it's very critical in terms of the response. You need to do immediate action. Then you use this feedback path compensator, whereby the compensator you locate it here. So basically, this is to avoid time delay and lag, meaning that the point I given you here, is to give you the convenience of which controller you want to use, what kind of problem you have. You know better about the problem, okay? So you use a time delay lag compensator, because when you don't want to, because you might understand, for this control action to be taken here, it takes time, you know. You need time for example, you're talking about digital control, you need time to convert from analog to digital. You need time also for the control action, and then you need time also for digital to analog. And if that is critical, you use this feedback pass compensator. You put the compensator directly after the sensors. Okay. So if you're talking about, you know, this is your input, but sometimes you have also disturbance. Disturbance can be external factors. You want to tackle this disturbance, and you anticipate that, for example, you are driving a car. You anticipate that in the front there, it is a climbing hill slope. Meaning that you anticipate this will be a kind of disturbance. Then you put the compensator in this form. And then if you're talking about to eliminate a minor disturbance, you can put a compensator in the inner feedback. And if you're talking about velocity feedback, you're talking about in instantaneous time from your plant, then you're talking about here. You use this velocity feedback. So, Stephen, basically the type of the compensator you use is depending on your problem. So that is my answer to that question. Okay, Stephen, am I answering your question?
Yes, sir. But to iterate more regarding this, for the topic on the PID controller, where you mentioned how certain compensator types, they reduce the steady state error, go to zero steady state error. Can you explain more about that one? Which one would have to be?
Okay, very good. Okay, now I'm talking about this PID. Okay, when you're talking about PID, there is three components there: proportional, integral, and derivative. Okay, there is three parts there: proportional, integral, and derivative. Proportional is good because it gives you a fast action. Okay, it gives you a fast action. But in order to get a zero steady state error, you have to have a high gain, just like here. In order to get a zero steady state error, meaning that your output is equal to 1. If your input is 1, your output is 1. In a control system, it follows what's your input. If your input is 1, you get 1. That is a very good control system. Okay. If your input is 1, you get 1.05. It's not good. That means you have a 5% error. Okay. But if you see from this transformation, you see that Kp over 1 F plus Kp. And this F is a friction. And friction, as you know, it depends also with time. Sometimes when it is hot, the friction is higher. Okay, so basically you have to control the value of Kp. And we know that this value of Kp also, if you increase so high, it becomes unstable. To ensure zero steady state error, you use an integrator. But integrator is very slow. So you use a proportional and integral to tackle. But there is a time you have overshoot. And your system cannot sustain a high overshoot. So this is where you use a derivative. So the combination of proportional, integral, and derivative will give you a very fast response, zero steady state error, and a very less, a very reduced effect on your transient response. So you see that the combination of the PID will give you all this effect. That's my answer, Stephen.
Thank you, sir. I got a better understanding.
Okay, thank you, Stephen. Okay, good. How about the others? Please ask question.
Okay, the others.
Not for now, sir. Thank you.
There's one question.
Yeah.
subject industrial automation and control more focus kepada actuator and pneumatic, PLC, robotic and control. Last part
So,
cover
Prof.
basic control. Nanti ada subjek lain detail. Ada
So
subjek.
that one, Prof, message to you, Prof.
Yelah, saya tak faham ni.
To apa ni, this subject is more focused on the pneumatic and actuator, motor and sensor. The control is the last part. So for the 4th year, the student will cover another subject for the detail on the control. So in this chapter, they have only one chapter and the last to cover the controls, basic control lah. So that's why I invite Prof to give in this topic.
Okay.
Maybe the student, some student maybe first time to hear the principle of the control itself.
Oh, see. Okay. Understand. Okay, understand. Okay.
So I think that is a very good experience to them to learn the control system, and then hopefully this is can gain more knowledge, experience to face in the new topic in the 4th year itself for the control itself. Yeah, Prof.
Okay. Yeah, correct. Okay, good. No problem. I think it's good also.
Yeah, it is good also.
Oh, meaning that they will cover the control theory later.
Yeah, because this subject is industrial automation and control system. So all the control is related to the pneumatic. We have a pneumatic lab for the using actuator, sensors.
Good.
So we don't have a PID for tuning, for lab, everything like that.
Understand. So basically, it is basically just on and off control.
Discrete control. So last week we already covered for PLC and then robotic for this subject. So that's why they already learn the discrete control for the on-off types control.
Okay, understand.
So any question other than that? Kalau tak ada, kita close.
Okay. Alright. So kalau tak ada tu lah, Dr. Zunaidi, I like to express my gratitude lah for allowing me to share with the students some of this one. So I hope student will get benefit from what I presented. And of course, as I said to you, control theory is a very important.
Yes, very important.
In many applications. Okay. So I wish you all best. I hope you will become a very prominent engineers in Brunei, and wish you well. So hopefully that if you were to come to Kuwait,
Thank you, sir.
please visit me.
So
Okay,
before finish, Prof, we take a photo session.
Sure.
So can we on all the camera, please?
So let me I put myself in my most handsome position.
Yeah.
Okay.
So
Prof,
Prof,
I like to see everybody.
Stop sharing the screen, Prof. Stop sharing the screen, first.
I stopped sharing the screen. Okay.
Okay. Can you on all the camera, please, everyone?
Yeah. I would like to see everybody.
Yeah, we can say hi to Prof and then take photo.
Hi, everybody.
Okay, everyone. You now in the classroom, huh?
Oh, you're in the classroom.
Some in the classroom. Okay, good.
Okay. Alright. Thank you. Let me take also my I want to put my print screen.
Okay. So now Wafiq, stop makan dulu. Okay, everyone. 1, 2, 3. Okay. With that, one more. 1, 2, 3. Okay, with that, thank you very much, everyone. Thank you very much, Prof, for giving the lecture today. Hope you can come to Brunei.
Inshallah. Thank you very much.
After COVID, Prof.
Okay, after COVID, I will come. Inshallah. Okay, bye-bye. Assalamualaikum.
Okay.
Very good day.
Yeah, happy Ramadan also, Prof.
Bye-bye.
Bye.
Assalamualaikum warahmatullahi wabarakatuh.
Kamu tunjukkan semua menyimpang.